We are live, sir.
ओके
नमस्कार, सुप्रभात। आप सभी का स्वागत है पीआरएल के अमृत व्याख्यान के 114वें अध्याय में। I, Anil Bharadwaj, very warmly welcome you all to PRL's Amrit Vyakhyans 114th episode. We started the PRL Amrit Vyakhyan on 4th of August 2023 with a sankalp that every Wednesday at 4 p.m. we have the PRL Amrit Vyakhyan. These Vyakhyans were delivered by distinguished speakers in different disciplines of science and technology, as well as in law, management, arts, sports, humanities, music, and whatnot. We completed this 75 episodes uninterruptedly in early January 2025. And subsequent to that, we started with the PRL Amrit Vyakhyaan 2.0 with a sankalp that every month we will have one PRL Amrit Vyakhyaan. Today, that is 23rd of March 2026, we have yet another very distinguished Vyakhyaan Karta with us today, Professor P.N. Goswami, who is Honorary Professor of Excellence and ANRF Prime Minister Professor at Guwahati University. He is going to give his Vyakhyaan on second revolution in weather and climate forecasting. Where do we figure? As we all know, weather and climate are two buzzwords which have been in the domain of science for several decades, and we still have to understand how do we connect and what are the implications of changes in weather affects the climate, and ultimately climate affects the humanity. I thank Professor Goswami for accepting our invitation and to be with us today for the PRL Amrit Vyakhyaan. I would now request Professor Pallam Raju to kindly introduce today's Vyakhyaan Karta to the audience on the WebEx panel, as well as those who have joined us live on PRL's YouTube channel. Over to you, Professor Pallam Raju.
Thank you, Professor Bharadwaj. It is indeed a great pleasure, honor, privilege for me to introduce one of the illustrious alumnus of PRL, Professor Bhupendranath Goswami. As was mentioned, Professor Goswami is a distinguished honorary professor and is a distinguished Indian atmospheric scientist renowned for pioneering work in monsoon dynamics and climate predictability. He was born in 1950 in Assam and did his BSc and MSc from Cotton University and Guwahati University. And then he joined PRL in 1971 for his PhD, wherein he completed his PhD in plasma physics. And afterwards, after 1976, he left to MIT and NASA GSFC for monsoon modeling. And his career includes key roles at IISc Bangalore as a professor and chair of the Center for Atmospheric and Ocean Sciences. Later on, he went on to become the director of the Indian Institute of Tropical Meteorology, Pune, and for over 8 years, 2006 to 2014, where he transformed the institute into a world-class organization. As the director of IITM, he led the Indian monsoon mission, and then bridging a 30-year gap to align India's weather and climate forecasting with global leaders through Ministry of Earth Sciences supported infrastructure and model developments. He contributed. His contributions feature transformative insights into monsoon variability and sub-seasonal to multi-decadal scales, including highly cited papers on the Indian Ocean Dipole, which has over 6,100 citations of the paper which came in Nature in 1999. And extreme rainfall, again, has around over a few thousands of citations with over 200 publications and H-index of 71 and over 29,000 citations. He's a highly sought after scientist who has contributed immensely, as one can see very clearly. And he is a fellow of all the three fellowships of Indian academies, and also the third World Academy of Sciences awards. He's the Shanti Swarup Bhatnagar Prize winner and Assam's Life Achievement Award in 2018, plus several roles on committees such as World Climate Research Program and visiting faculty at Princeton and Maryland. He has profoundly influenced the national climate policy. With these few words, I invite Professor B.N. Goswami to deliver the 114th VRL Amrut Vyakhyaan on very thought-provoking and very insightful title itself. I can see very it's going to be exciting, which is the second revolution in weather and climate forecasting. Where do we figure? So, over to you, Professor Goswami. So you
Thank you very much, Professor Purnamraju, and thank you all for inviting me for this talk. And as I said, I have a very close and emotional link with PRL, and this also happens to be the 50 years since I joined this. After my PhD in climate in plasma physics, I changed over to weather and climate, and that happened in PRL. It's exactly 50 years ago. And today, talking about that opportunity led me to work on weather and climate and be part of this first revolution of weather and climate. And so it is, and this second revolution is happening now. And but I have been sort of been fortunate to be part of that revolution, first revolution. And it is indeed an honor and privilege to talk about that today. So let me try to share my screen.
Sure.
Okay. So
Yes.
okay, is this visible now?
Yes, it's visible.
Okay.
You can.
Okay, I'll make it full screen. Okay. Okay, is it all right?
Yes. Yes.
Okay. 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 So I like to start with this slide where this in 1923 to 2023 there is a paper published in Science which they featured in their cover page, and that paper was related to weather forecasting using artificial intelligence and deep learning. They thought that this is a groundbreaking work, and obviously it made a big news. And the next year, NASA, when they tried to sort of see what are the science events, science research that actually made the biggest news, they found 10 of the top science papers or research that made big news, and this was one of them. So indeed, that is when actually the second revolution of weather and climate forecasting was initiated, and and that is so within 2 years of this publication, that paper is now cited more than 1,200 times. That is the impact of that work. So I think that is how the whole revolution of the second revolution started in 2023. Of course, this had happened because of AI advances in the AI technology, and that is why I think the AI is making tremendous impact of how we do science research today, and how additional benefit can come from this application of AI technology to the science and technology, especially prediction, like weather prediction. So, and for that, 2024, the Nobel Prize in Physics went to the AI scientist. So, so to give a context of the weather prediction and how the benefit of weather prediction has changed our lives, let me start with this recounting that for a long time, people like me, we are always, even if we are doing basic research in weather and climate prediction, we are called weathermen, right? Weathermen have been the favorite subject of cartoonists for a long time. In fact, I have gone through that for a long time. But in the and because our forecasts were not very good until recently, we're still struggling to make better forecasts. Of course, it's because this weather forecast is a very difficult problem. So people are all making fun of our forecast, and but interestingly, if you see recently, things have changed. But in recently, have you noticed that the cartoons and jokes on weathermen are conspicuous by its absence? So you don't see, even in the social media, you don't see people making fun of the weathermen. I think this is a big change, because fun of weathermen used to be the favorite cartoon all over the world, including India, of course. Um, uh, uh, but that is because the perception of the general public itself has changed about weathermen, and the weather forecasts have changed for the better. And how did it happen? This happened because the weather prediction, the quality, the skill of weather predictions have steadily improved and reached a stage where now we are much better. So this is a figure that I have borrowed from. This is the skill of weather forecast, this sort of history of skill of weather forecast from 1980s to present, from one of the leading centers of weather forecast in Europe called ECMWF. They have kept a history, and it shows that this is plotted, this kind of correlation between the observed patterns of lows and highs and the forecasted patterns. And if they are very, sort of 99.8% correct, means all these lows and highs are properly placed with intensity and phase. So that means the weather prediction is highly accurate. And so these are the first curves are for 3-day ahead of forecast, the 5-day ahead of forecast, and 7-day ahead of forecast. These are like 10 days ahead of forecast. So these forecasts have increased from 80%, the 3-day forecast have 80% in 80s to about 98% today. The 3-day forecasts are that good. In the extra tropics, the tropics is slightly tropics, the weather forecast is a little more difficult, and it is a little less, but still we have made tremendous progress in tropics also. But this is an illustration of how it has improved. So it is almost perfect, this forecast. So 1-day forecasts are almost perfect. 3-day forecasts are also almost perfect today. But the progress is that in 80%, it used to be 80%, now today it has become 90%. So today, now 7-day forecast ahead are as good as a 3-day forecast in 80s. That means over the years we have improved by this. It took so many, about almost 70 years or 40 years to make that much improvement. So 4 days gain we have made over this, so we can make 7 days ahead to kind of forecast that we could make 3 days ahead in 80. So that is the kind of improvement. So this has translated into a lot of benefits to the society, and people are now more comfortable about this weather forecast, and you can make better decisions based on them. So that is the reason why today people don't make fun of it. So, but the story of this, how it happened, took long time. It was, the first revolution was very slow. It started way back in the early 20th century, when people recognized that for aviation we definitely need a forecast. But then in 1920s, it started with a failed attempt by Louis Richardson and British mathematician. He later worked in the wartime. He worked for the government, and then he wrote a book in 2022 trying to solve the basic equations using numerical techniques and advance them in time and make weather prediction. So, but he realized that should be possible, because the basic the weather is essentially follows some physical laws, and those equations are known. So now if I could integrate them and advance them in time by numerically at least, then because these equations are very complex, partial differential equations, coupled and so on, non-linear, it's very difficult to solve analytically. So you need to solve them by numerical techniques. So he tried that, but actually he produced some forecasts, but forecasts were very erroneous. They were very and he failed because he failed to understand some of the basic sort of limitations of the technique that he has used. He has wrongly used a sort of equation which will be small errors in this in this sort of imbalances in the initial state will grow and blow up into big weather kind of system. These are like produced by gravity waves that was imbalance in the initial conditions, and then in nature they will disperse away, but in the numerically when they solved, he found a lot of weather like cyclones like happening every 1 hour or 2 hours. So this was a mistake, but that then people recognize, tried to understand. But it took another 30 years to make the first successful numerical weather prediction in 1950 at Princeton University under the leadership of Professor Jules Charney. That Jules Charney was a big theoretical meteorologist, and he actually over the years did a lot of basic research to try and understand what are the problems with these equations. Trying to when you try to make predictions, what are the problems that lead to these problems of errors in the forecast? And he realized that if we can modify the equations in a slightly more simpler way, then the weather forecast will be easier. That is called the quasi-geostrophic equation. So he developed those equations, and so he was brought to, when the first numerical first computer was available, von Neumann was he's another visionary at Princeton. He thought that okay, now the computer is there, now the basic sort of the framework for doing forecast is available. So he brought Sarni to Princeton, and they had a small group, and they did the first weather forecast on a very regional scale. This ENIAC was, of course, a very small. I mean, today's time, this I think the memory and the disk is available in your smartphone. Is like that computer, and using that kind of a computer, they made the first forecast, and they were quite realistic, and they saw the feasibility of actually making that kind of a forecast using numerical techniques. And using some of the basic simplified basic equation. And so I was fortunate to work with Professor Jules Charney as a postdoc for a couple of years at MIT, and that was another inspiration for continuing this work in climate and weather and climate science. So this has taken over the next 50 years, next 40 years. The models and the computers improved, and the models also improved, where we could make better and better physical formulation of the physical processes, and the revolution progressed. And this revolution is now, has come to sort of a mature stage where it is summarized in a review paper in Nature a few years ago. Very nice papers. People can see this. I'm quite impressed by that paper. So it took more than 60 years from 1950, and a quiet revolution, and hundreds of dedicated scientists and for the skill of weather forecast prediction to reach the present stage. So before I go to the second revolution, I need to tell you what was the first revolution. What is the kind of weather prediction system, and how we could improve the system? The improvement of the weather prediction requires a couple of things, which I'll just describe in a few minutes, because the improvement of those required a lot of basic research, lot of work, and that work slowly and steadily improved the forecast. And but today it appears that using the numerical weather prediction route through which we made the revolution, the first revolution, made progress, is now reaching some sort of a saturation, and there we need a different revolution to overcome the problems faced by the numerical weather prediction. So that is what I'm going to talk. But before that, I need to give you a background on what is the weather and climate prediction system, what is entails, what is required to improve this forecast. Now, so weather forecasting is essentially has a forecast model. The forecast model is based on some physical equations. These equations have these natural variables, the wind, temperature, humidity, and pressure, and rainfall. So these variables are progressed in time, and these equations can be integrated in time, and time marching can give me forecast. But for that, these equations have to be solved over the whole globe, because over the whole earth, because that is the fluid system sort of is an envelope which is and they interact each other with each other, and therefore we cannot solve the weather problem even for Ahmedabad or Guwahati. It is affected by things happening elsewhere, and therefore we need to solve the equations everywhere. And so the solving the equations over the global domain is very important. So this is one issue. Then where does so these are equations which have a time mass. That means the initial value problem. So initial value problem equals initial conditions, and initial conditions means initial state of the atmosphere in terms of the winds, temperature, humidity, and precipitation and pressure, and that must come from observations, and that comes from all the observations. So if I have the observations, I can then analyze them put them into regular grid, and then solve the equations into this. So there is a kind of observation don't come on regular grid points, right? Observation come arbitrary positions and things like that. So finally, you have to sort of do the proper analysis and interpolations or whatever is required to put them into the right into the uniform grids. And that is the initial condition. Once that is there, you can crunch it with the computer and then advance in time, and then you get the solutions which are given with the forecast. So that is the basic framework. That framework requires at the core of this framework is a dynamical model. So dynamical model means solving the equations. That is a dynamical core. But dynamical model has basic equations. These are the equations. So these equations are basically the normal Navier-Stokes equations. I don't want to go into great details, but a couple of things are important. So these equations are forced by heating. So on the right hand side, these terms represent the heating and dissipation. So it is essentially atmosphere is forced by heating, and then atmosphere produces response to the heating. Heating and response are produced in terms of waves in the atmosphere. This wave propagate and then produce system. And when the wave propagates, sometimes some of these waves become unstable due to local feedback, and that produces our systems. And then they get, as they propagate, they dissipate, and so therefore there is a quasi-equilibrium is maintained. So that is how the whole system keeps evolving in a dynamic equilibrium. And that keeps happening, and that is weather. So the systems, when the heating produces waves, these waves become unstable, and that unstable waves produces main weather system. And so, and that is how things happen, and we have to simulate them. So this forcing, that means the heating is our main the driver. Now heating comes from three different sources. One is of course the solar radiation, and that is coming, and that the radiative balance becomes a part of heating. But there can be within the system, there can be evaporation, and which will take away some heat, but the precipitation, condensation will release latent heat in the atmosphere. So therefore the heat balance in any parcel of air will depend on the proper calculation of the heat balance in every parcel of air, every grid box. And that is the most complex problem in our forecasting. So that comes from all kinds of processes in the atmosphere. There are atmospheric aerosols that will produce some chemical reactions, and they can contribute to the heating. Radiation budget is the main. Therefore, there is the literal mixing of grid boxes are the basic dynamic processes. Then there are moist processes like how clouds form, and how that produces latent heat, and how evaporation can take away some of that heat, and so on. So, and therefore there is also the turbulent mixing at the boundary layer, and the turbulent mixing can add some moisture into the atmosphere, or even heat sensible. A part of heat can go into the upper layers, and so on. So, and then finally even the ocean can affect our atmosphere, because through the sea surface temperatures, it can affect evaporation. Evaporation will then produce more or less moisture into the atmosphere, and that moisture can again affect my heat balance in this. So there is a whole lot of processes which contribute to it, and all this we have to formulate in the model. And that solving the model themselves have their own challenges, because now to make a accurate solution of the solution of the equations requires smaller grid sizes, because the numerical solution is more accurate when you solve them in a smaller grid sizes. And then so you need to increase the accuracy of the solution. I need to go to finer and finer resolution. But going to finer and finer resolution actually increases my computational expense. And in fact, it increases by a factor of, if I increase double the number of grid points in the globe and in the vertical direction, it actually, once you go to a smaller and smaller, you have to use a smaller integrations time step to be accurate, and that makes your computation time go n to the power 3 rather than n square. So that is another big challenge. So you need better and better computers to make better forecast. That is one thing, but that's not good only enough. That is only equation. But actually, accurate physics is much more important. Physics, as I said, is coming from a whole lot of different processes, and each of the process comes from very small scale physics contributing to large scale weather systems. So the models have a resolved scale. Models can never be, depending on what are the computer that is available, your model has a limitation of what resolution what the scale you can resolve. So suppose my model is about 20 kilometers by 20 kilometers. Now within 20 kilometers by 20 kilometers, there are clouds that can form, or the turbulent processes that can form. All that can affect actually my heating. So how do I formulate that? And that is our whole major problem. So all these different components of the heating which contribute to the equation has a multi-scale interaction, and that interaction gives rise to, because very small scale also contribute to the larger scale. So in the resolved scale, my large scale fields are that 20 kilometers by 20 kilometers, my large scale fields are solved. But to get the large scale solved, I need to get the heating function. Heating function is now contributed by very, very small scales within this large scale domain. So how do I formulate that? And that requires interaction between this understanding of how the small scale affect the large scale and the large scale affect the small scale. So that understanding is the key process for improving the forecast. So for example, this in the case of clouds, if you see, the clouds get into the moisture forms into condenses into small droplets, and from small droplets this moisture then forms small droplets are organized into these cumulonimbus clouds, and so in that cloud scale also heating is released, but initially they are individual condensation this thing can also produce some heating. So I have to figure out how these small scale condensation nuclei are actually contribute to the heating within a cloud. But then the clouds are then organized into these cyclone type of weather systems, and then cyclone type of weather systems are then organized into these large scale planetary scale intertropical convergence zones type of systems. So for larger systems and the climate, I need to calculate the heating over this whole very large 10,000 kilometer scale. Okay. On the other hand, for weather, I need to calculate the heating on this 1,000 kilometer scales, and these clouds are about 1 kilometer or 10 kilometer scales. So, and the condensation nuclei that is required to form the droplets are of in a micron scale or even submicron scale. So we have a range of scales which interact to produce my heating, and therefore I have to understand how they interact so that I can formulate these heating in those resolved scale. And that is, so we are talking about a range of scales. Horizontal scales spans about 15 orders of magnitude. So this is a huge problem in our field. To improve the physical formulation of the heating function in the models requires some approximation, and those approximations are what we call parameterization. In those approximations will always lead to some error in the model. So models can have error, and the model errors will also affect my forecast, because model errors, every time you integrate the model errors keep building up, and so the model errors are actually more serious. And there is always a limitation on how far you can go in improving the models, because we cannot solve all the Navier-Stokes equation on micron scale over the whole globe. It is simply not possible. Even if I have a supercomputer, I cannot do that. And so we need a simplification, and that simplification means that there will be always a some error. So our forecast will never be perfect. There is nothing like a perfect forecast, but how can I improve them, and how far I can improve them? And there is always going to be a limitation on how far I can improve them, and that is a so to get that going. So we need, so there are two types of errors that are there in the forecast. So one forecast error will come from the models. The other forecast error will come from my initial condition, the initial state. The initial states will come. Initial state is it comes from the observation, but the observations have a lot of limitations. For example, the ground observations have over the ocean there is no observations. The profiling of the upper atmospheric profiling also have a mostly located over the until the satellites came, the profiling of the atmospheres are all limited over to the land regions. And then therefore our analysis had lot of errors. Now with the satellites now, this has improved considerably, but still there is a lot of errors. Because I cannot complete a 10 kilometer by 10 kilometer global model. If I have every 10 kilometer, I cannot have all the data. Even with all the satellites that you have, you can never have it. So therefore, always you will have some error in the small scale. Large scale, maybe now we can actually do and initialize it quite well, but still the small scale errors are still there, and those small scale errors actually affect the large scale errors again in the future. And the other problem that is there in this model, our system, is what is called due to what are the deterministic chaos. For example, some systems like tides and planetary position, they can be predicted years and ahead of time, right? Because they are determined by equations which are algebraic in nature, or very linear equations which have no dependence on errors in the initial conditions. They can simply be, if I know the initial condition, I know what will be the future state. But atmosphere is not like that. Atmosphere is a chaotic system, so it is what is called deterministic chaos. It is determined by a real physical equations, but its future evolution cannot be predicted because it is very sensitive to initial condition. A small error in the initial condition can grow and diverge from the actual observed trajectory significantly after some time, depending on the rate of growth of these errors, which is determined by the nonlinearity in the system and the size of the error. So this is what is the chaos is what limits our ability to predict. And so that also depends on the initial error. If the initial error goes down, is reduced to very small values, then the growth of errors will be slow, and therefore I can extend it to certain level, beyond which again these things will limit. So there will be always a limit on my deterministic predictability, and that limit was estimated way back by Lawrence in that maybe the extratropical weathers will have about 2 weeks is the maximum time that we may be able to predict them. And so that was the theoretically calculated and then tested with models and so on. Roughly that was established them. So we are trying to, by using models, we are trying to reach that limit. And that is what happened. And how did we try to improve that? By reducing the initial error, by improving observations and improving the balance between the equations and the observations in the initial time. What happens is that even if whatever observations you have, the observations are never fully balanced with the equation, because there is always some error. Now, so So when you put the observed variables, observed data into the equations of motion, then you see that if you try to balance the left and right hand side, it will not balance because you get errors in calculating all the terms because of the errors in the observation. So as a result, there is an imbalance in the always there is an imbalance in the equations and what comes from the observations. So this imbalance actually the model sees that as an initial error. So the one way to do improve the forecast is to how to reduce this initial imbalance. So that is what is done by what is known as data assimilation. So I do the analysis is the first step. Then I do data assimilation into the system so that I try to reduce the imbalance between the analysis and what is required by the model. And by that way, we could reduce the initial error. So that is how by improving. So data assimilation is a big field of how to do this. And so that way, slowly and steadily, we have been able to we have been able to reduce the initial error considerably today, because now there is good amount of data that comes from the satellite and the techniques of data assimilation have improved. So together, that part initial error has reduced considerably. But still, as I said, in the small scale, there will be some error. But the model errors were the bigger problem. And that by those parameterizations processes, the physical the sort of understanding of how the small scale and the large scale interact, and based on that, how by formulating that heating function and heating and dissipation function and the resolved scales better and better, we have been able to now, and that required a long time. It was a very slow process. That is why the first evolution was rather slow, because it took long time to slowly and steadily improve these physical processes. And of course, computers also played a role. And then, of course, now with better computers, we can improve the resolutions, and that also have now contributed to this. So also these two things, improvement of parameterization and improvement of resolution, both contributed to the improvement of models. So both this model error reduction and the initial error reduction led to improvement of forecast. So all these things were contributed by three fronts. Better and better observation, three things mainly. One is the better and better observations from space, especially from space, and better the great improvements of the models in resolution as well as complexity, as well as improving the formulation of the physical processes. But it could not have been done unless the computers were available. Now computers also have been available, and in India itself we have been now able to get. So when I joined IITM, there was nothing actually in the country. But by the time I left IITM had a 800 teraflops machine, and slowly country is now having teraflops machines. So therefore, computer-wise, I think today we are okay. We should not complain. But it is the thinking that how to utilize the computer properly is where we are lacking, I think, still. So the first revolution came through the numerical weather prediction route, and it got improved because of reduction of the initial error and improvement of the model prediction model errors. So why do we need a second revolution? Second revolution was required because NWP has reached the numerical weather prediction has reached a crossroad. What is that crossroad? That is why we need. So what is that crossroad? Let me talk to you about that. But this is the reason I am talking about the second revolution is another reason is that in the first revolution we clearly missed the bus when the first revolution was taking place in India, and today the second revolution has started. But even I see that we are not seeing it. And taking that opportunity to how to capture that sort of momentum and take leadership in this second revolution. But we are missing that also today. So that makes me very concerned, and that is why I want to talk about it today. So what is the crossroad that I'm talking about? One is that, as I said, there is a limit on deterministic. If I have to use the equations of motions and then basic equations and integrate them numerically, and then because of the small errors in the initial conditions, it will always be limited. So there is a limit on deterministic predictability. And it seems like that we have arrived at that limit almost today, because I'll show you that. So you see that in this is the skill of improvement of the skill, and you see this skill of, for example, 7-day forecast over the last 10 years, it has not increased at all. And 1-day forecast or 3-day forecast cannot increase because it is almost it reached at least how much it can achieve. So here in the 7-day and 10-day, we have to see how can we improve this. Now, if you see the 7-day or 10-day forecast, they have not improved at all in the last 10 years. Although models and data simulation have improved, still they have not improved. So it looks like that we have come to the sort of limit on achievability due to deterministic numerical order prediction technique, because of the small errors that are still there in the initial condition, and that small error will grow. Small scale error will grow rapidly and become nonlinear, and then interact and cascade through nonlinear interaction to the larger scale, and even the larger scale motion are now is being limited because of the errors in the small scale and because of the growth of errors in the small scale. So that is and that is where the artificial intelligence and the deep learning models comes to rescue. And the second revolution, the weather prediction, actually kick-started in 2023. And that is when in 2023, we got in that particular year about 3, 4 or 5 papers, some landmark papers appeared in literature, and they all showed that if I can use the artificial intelligence and deep learning techniques and train them on observed data, observed weather data, if I have a good observed weather data, I can predict the weather events like the lows and highs in the extratropics and even tropical cyclones much better than the best of the numerical weather prediction models, which used all the physical equations and the physical processes and so on. So those models have evolved over the first revolution, and they are still now getting limited, but that limitation it can be overcome by these AI deep learning model. These are data-driven model. These are not based on equations. They are like pattern recognitions and training on those patterns, how pattern of today is affected by was related to the pattern of yesterday, or pattern of this hour is related to the patterns of last hour, and so on and so forth. Like that, if I can train the model on good data, then today I can predict actually better large scale motion, large scale weather systems than this. So this is a big thing. And this happened in 2023. I will not go into great details of the techniques and so that, and I'm just talking about philosophy, why and how it was possible. So why did it happen in 2023? The two important developments happened. One is that until then, all the weather prediction models, weather predictions, until recently, all the weather prediction centers are doing this data analysis and assimilation every 6 hours or so. And so, and all the data that the previous data on which I have to train, they are called reanalysis. So normally such a model is taken and you go back in time and analyze again using a good model, and systematically with the same model, then you analyze again throughout the whole period of time until today, and create a set of data which is now surrogate observations over the 3-dimensional observations over the whole globe, which serves as a observations, better observations, and then consistent and better observations. So earlier, what happened is all our reanalysis was like 6-hourly analysis, but weather systems actually develop in 1 to 3 hours. Many of the thunderstorms once evolve, die in 1 or 3 hours, and then another one events. And so 6-hour gap doesn't resolve the weather systems correctly, and therefore even in my large scale weather systems I will have errors if I cannot resolve the weather systems correctly. So we need analysis of a long period for reanalysis for a long period with 1 hour. 1 hour reanalysis was required. It was not available. Only in 2020, European Center had produced this 1 hour reanalysis for 1940 to 2017. And that is when I think these computer scientists realized that, well, we have the good data now. We can now use these techniques to predict. And by that time, another thing happens in the computer science side also. There is a three-dimensional. See, our weather systems are all three-dimensional, so we need three-dimensional pattern recognition technique. And the three-dimensional pattern recognition was still lacking until very recently, until when the vision transformers had come in. And so the vision transforms also happened around the same time, and the people in the community realized that, well, this is our opportune time to apply this, and that is where some of the private companies actually invested good amount of research, and as a result of that, 2023, all these papers had come in. So these two measure the availability of hourly analysis and the vision transformers are. And this paper, that is why, became one of the most cited paper in the history. This by an Indian Indian scientist leading this work. When I first saw that this title of this paper is "Attention is All You Need," I did not know what attention is. Why? I thought it was just a poetic name. But actually, in computer science, there is a very important distinct. Attention is a terminology to say something about how you train these. So I don't know much about this the inside of this, but I'm just learning some of those. So this paper has actually, how this AI techniques has now revolutionized science and technology research is that shows that this paper is now in 2025 when they revised the list of the most cited papers in the last 100 years, in that, if you say this paper is ranked 7th in that top, so that is a big achievement. And within the next after the new millennium, after 2000, it is the top most cited paper anyway, all science. So this is very interesting. Many of the top cited papers happens to be techniques rather than basic science. So I think this is the same thing that even in this top cited all over, this is a reagent that affects the biochemical analysis and so on. So this is very, very interesting, and of course it is evolving, and many people are now concerned about it. So this is one of the, so how the AI technique has sort of become overwhelmed everybody. So this is one of the top AI scientists, Yoshua Bengio. He has worked on this generative adversarial nets, and that paper is cited more than 1 lakh time. But his total citation is one of the first person whose total citation has crossed 1 million citations. So that is coming from the AIs, you see. So that is where the science is heading. So this is the example of that paper that I mentioned in the first slide. So this paper actually has shown, this is the result. This is just to give you a very brief result showing how this compares with this. HRES is the high resolution weather forecast coming from ECMWF. This is the physical model, and this is what is called as the forecast lead time going from 1 day to 10 days. At how the root mean square error between observations and predictions are increasing. Increasing root mean square error means bad forecast become poor. But if I use the GraphCaster, this is the neural network model. Neural network model actually has a neural motor has low RMSE, means it is better compared to the high resolution model. Same thing, the correlation between the observations and the is higher is the better. So the GraphCast model has higher correlation at longer leads, at not at short leads. So the longer leads means that at longer leads it can somehow avoid the error growth problems. Okay, so it is the error growth is what is limiting the long lead forecast, and this is the AI models are able to overcome some of that, and that is the interesting part of it. So how they have improved the error growth problem? So one of the ways is I can think about is what is like these pattern recognition techniques are like finding analogs. You know, see if all these LLMs and the large language models, etc., are nothing but analogs. So what they do is you have a string, you have a pattern, or you ask for a string of questions or whatever. That is like a pattern. Now they find out in the past, in all over the data, how many times such patterns have occurred to what sort of closeness, and then what follows that is your forecast. So that is kind of in observations also. If I have excuse me. So our observed system also follows by the the weather systems follow the physical laws, and therefore if I find out what happened today's pattern, if there is analog in the past, and what follows after 1 hour will be my forecast, because it has that pattern has changed after 1 hour, whatever it changed to, and that will be my forecast. So that kind of, but if I can find out good analogs, I can make analog forecast, and that is actually was envisioned by Professor Ed Lawrence way back in 70s, 60s. But at that time he did not have much data, and therefore he could not find any real good analogs. But today we have so much of data, we can find good analogs, and we can actually make some analog forecasts. So it is some of these the training is some sort of an analog finding. But these models have certain critiques, because the physically our system follows the basic laws. The basic laws, but the pattern recognition pattern recognition technique does not require any laws. So it finds just the pattern. What is the relationship between the pattern of this hour with pattern of the last hour? So 1 hour difference, if I know that, I can use to predict for the next hour. So it finds that relationship based on all the data that I have. So that is, but it doesn't care about what is the dynamics that goes on. But actually our system is following the dynamic. So our forecast should be more like probabilistic rather than this deterministic. This is not. This is completely deterministic. It is like predicting tides, but it is not like predicting tides. It is follows our dynamical systems. And the dynamical system has non-linearity, and we have to somehow make them more realistic. And that is one issue. The other important issue is that these techniques are still cannot produce the rainfall forecast. They have not been able to. Large scale very good, but rainfall they cannot, because rainfall have a lot of small scale variability, and the small scale variability in rainfall requires much larger volume of data to be trained, and they cannot find all the possible relationship between 1 hour pattern. 1 hour pattern itself is a very, very complex pattern, and that complex pattern, how it was linked to the 1 hour before that, and there are possibilities of different possibilities of this relationship is very large, so large that I need a large data set to train, and that has not been available. So this is a big issue that is still a remaining issue, and the work is going on that. So what we need is a long hourly reanalysis with using something called the non-hydrostatic model, so that I can have a good data set to train, and that is still not available. So we have to now think about how to include precipitation into this data and improve their forecast. But one important thing is that all these forecasts should be something called hybrid mode, so that you don't just use the just use the patterns and then make predictions just based on how patterns are related with each other. Instead, you make them go through a dynamical process so that it heals the evolutionary history in some sense. So that is actually being done. So recently a model that is now is sort of neurogesium, they call it neural gesium, so which uses a in between step in which the patterns, initially the data is used to convert the observations into patterns, and then patterns are then fed to a something called ODE solver. And this ODE solver is essentially, ODE is not just ordinary differential equation. It has the kind of nonlinearity that we have in the system, and the advective nonlinearity, and this advection then moves the system to a different the appropriate direction. So and then what they do is that they actually calculated the heating tendency from another component of the model, which actually trained itself on the fine scale data of the heating parameters that produces precipitation or heating tendency. All the parameters that contributes to the heating tendency, they get high resolution data from a high resolution cloud resolving model, train the model on that to get the prediction on that the heating tendency on each of these each of these patterns. So that once that heating tendency comes into this ODE equation, then you use that ODE to advance in time. So it is still very, very cheap in terms of advancing in time, and is much more dynamically consistent. And so this also makes actually very good predictions. And so that is now advancing. So these are problems that are there, which are now slowly being improved, and now advance is taking place in a very rapid space. So finally, these initial predictions were based on analysis which were done by the weather prediction models, and so like the ERA 5 European Central Analysis, phase 5, those data they use, the analysis was already done. So the models were using that analysis and use the patterns in those analysis to train them. So instead, actually, if I have to use this data-driven model in the real-time forecasting, then I will have to, as the data comes in, I have to do the analysis within the system and then feed it into the data-driven model and then produce the forecast. And to do that, I need to integrate this end-to-end data-driven forecasting system, and that people are now doing that. That is also being done. So things are actually going to in a place where now we can routinely make operational forecast. In fact, let me. So what should be our priority in the country-wise? I think we should should think big and must avoid complacency. But we have this problem in our country that we think that we are doing great and we don't need to do anything else. So I think that is what is limiting our progress in catching up with this. So we need to think big. But like what? So actually we have so much of see all these forecasts that have come. Most of them are led by some Indian computer scientists. Okay, but India has so many great computer scientists, and we have sufficiently a good experience the weather and climate scientists. Why can't they build a foundation model of our own? Why can't we think about building a foundation? I have been associated with this AI mission from the government. There are hundreds of proposals have come, but nobody is thinking. We have somehow this Galgotia culture is now thinking is the sort of is paralyzing us. Nobody is thinking big and thinking of the original thing and just copy something, copy paste and do something. This is what is killing us. So I think we need to think big, and I don't see why we cannot do that, because we're not just thinking. And then why I'm saying is that and already this European center, which I was talking about as the leading center, now they are saying they have seen this. We are not, our IMD is also not seeing these things, that this is going to be our future. And so is European center has started 3 years back, and today they realize that, well, we unless we keep updated, we will be obsolete. And so what they did, they tried, they assimilate that into the forecast system, and now developed a better, faster, because the advantage of this, whether these AI systems, I mean, are such that once it is trained, making the forecast is very cheap computationally. It just doesn't take any time. And actually our operational forecast takes a huge amount of computational time. Now we can reduce that if I replace the forecasting part by these. But the developing part will still require a lot of development, lot of good data, and the models will be required. But we cannot get away with the model. So you have to have a sort of hybrid structure such that your forecast can still be improved and expand your forecast horizon by using this AI technique. And that will be highly beneficial for the users, and at a very little cost. And so, and they have recognized that, and they have now got a model which is this is recent, this is still in archive, not published yet, and they are now being able to predict even the rainfall to a great extent. So I think this is and in India we are not seeing this. 5 years ago, actually, I made a proposal to MOES for capacity building. I realized that this is going to happen, and we need to build capacity, because in the country there is not even meteorologists, none of the meteorologists even understand the complexity of this problem, and how to help these computer scientists, how to bring computer scientists to understand the problem so that they can help us. And that is missing. So we need capacity building in the community itself, the meteorologist itself, and that is not missing. Today AI missions have come, but you don't have people who can think about it. So we are going to miss this bus. So this is my problem. So this is the most I think my concern is, as I said, is that we are not thinking big, and because of this lack of vision, we missed the first bus of the first revolution. And when I joined IITM in 2006, and I was given this task of improving the forecast in this country. I come from ISC, where I did only basic research, and I did not, because the opportunities are not there actually to do research on actually improving the forecast. Computer was not there, so we had to do basic research. But those basic research have helped, because to improve the model, we need to have good idea of the basic processes. And those processes, when I joined IITM, helped me to improve the models. And so because and that is what is required. But to improve that 30 years gap, to bridge that gap in 8 years was like unbelievable task. It was impossible almost. I thought I will fail. But I was lucky that I had help, good help, and a lot of hard work from good help from ministry. At that time, fortunately, we had two people who was heading the Ministry of Earth Sciences, P.S. Goel, and for a very short time, but for most of the time, Silas Nayak. Both come from ISRO. Remember, this is important. ISRO thinking is what made me possible to address this question. The freedom that I needed and the funding that is needed was given, and that is what helped us to at least catch up with the world. And but it still always needs you have to, the forecasting of weather and climate is an evolving process. You can, as I said, the models are never perfect, so we will always have limitations. So we will have to work continuously on improving it, and the all weather prediction systems around the globe keep doing that. But in India, we are not doing that. We are not. As soon as I left, then some people again argued that we don't need to invest too much on model building, so let us go back and try to improve application. Then we missed it. Now last 10 years have gone, and we have not been able to make any improvement in the models. 10, 12 years have gone, and we have not been able to make any improvement in them. No new ideas have come. So I think we have these problems we need, and that actually is very detrimental for the country, because the country is missing the opportunity. our farmers are missing the benefit that they can get. It is our the scientists and the policymakers are not able to deliver what they deserve. And I think the second revolution will also miss the bus because we are not seeing this and we are going too slow. Because I see that I have been sort of been in some sort of an advisory capacity in some of the projects that are coming for this AI missions. So AI missions has a component of AI application to weather and science. Now, after 3 years of this progress in this weather and climate, we have seen now that okay, this is important. Now we should do something, but the thinking is still in a very sort of as a cavalier manner, so that we have to realize that this is the whole AI business is going to going to sort of improve in a sort of exponential scale. As a result, we have we have to think differently how to keep ourselves relevant and keep ourselves engaged such that we can be still relevant. Otherwise, we will not be relevant at all, because we will not be able to do anything that anybody will be of interest, because we will still we will be borrowing what others will be doing. So unless to do that ourselves, we need a big funding, and the funding is in capacity building as well as in infrastructure. But what I'm saying is that still we are not realizing that the kind of freedom that we need to execute this is not available in the system today. And I must say that that it is very slow, too slow, and it makes me feel that it is almost impossible. It will be almost impossible to catch up with it, because first of all, we don't have enough people who can think. Secondly, the whole process of funding and other things are so slow that it will not be able to catch up with this process. So with that concern, I will stop. And this is I had a small group who had helped me for my throughout this last after retirement. It was a challenge to do anything relevant, but I was fortunate to have a few students, PhD students and postdocs to help me in this endeavor. And most of them has left, but only one I have now. So it is still a big challenge to do anything good research in after retirement in the country. But I am fortunate that I am still getting some opportunity. Okay, thank you very much. So shall I get back to?
Yeah, no, sir. Just a moment. So,
Okay.
so thank you, sir, for very interesting and comprehensive talk where you touched upon the evolution of the forecasting system and also about the derivation on key aspects of the forecast which we need. And of course, we assume that there will be a lot of questions, and to moderate the question answer session, I invite Dr. Narendra Ojha. Are you able to hear me?
Yeah, I can hear you.
Yeah, Narendra?
Yes.
Yeah,
Yes.
so please, over to you, and please moderate the question answer session.
Sahuji, am I audible clearly?
Yes.
Okay. Okay, thank you. So thank you, sir. It was a very enlightening talk, and
Okay.
you presented a lot of new perspectives on AI. So
Yeah.
I request all the audience that if you have any questions, please raise your hands, and I will invite you one by one. And I myself have some question to you, so
Okay.
I will start with that.
Okay.
And
Please.
and sir, before I say put the question, I wish to inform you that at PRL we are doing significant R&D, and we are also looking at atmospheric chemistry.
Okay.
And some of our colleagues are looking at aerosol rainfall, which you highlighted a lot in your talk. They are looking at using similar methods like vision transformer. So it is at R&D level, and
Okay.
when you are here, probably we will get more time to explain to you.
Okay.
So
Okay.
so the first question is, sir, it looks like that we still have huge dependence of on conventional models and on larger observational data to to utilize full potential of the AI, to provide them what they need for better training. So so when we are making that type of data sets, so do you see that parallelly we have to keep on improving conventional models, especially when you say that for tropics the issue has been more?
Absolutely. Absolutely. I think we have to. We cannot abandon the model, because conventional models are the basis on which the data will be available. Better and better data will produce a better AI model. So, the only advantage is that now we need not do the operational part of forecasting by using these traditional models, because operational part of forecasting already requires a lot of computer time, and the skill will be, now if the skill of the AI models are better than those conventional models, then I can abandon the actual forecast part, and which will remove a lot of computational cost, and that cost then can be used to improve better and better data, conventional model. Improve the model, we have to continue to improve the models, and use that, keep that work, but still produce better long-term data for assimilation, or for training. How will that come? The best data for rainfall, and rainfall is going to be the most difficult problem, as I said. But all the analysis today, today we have this ERA 5 1 hour analysis, which actually made a big impact in developing all these models. But their precipitation, hourly precipitation, is very poor. We realized that we did analysis, and we found that their the ERA 5 precipitation, hourly precipitation, cannot produce the extreme events, cannot produce the extreme events that is seen in the observation. In fact, the observations, you get very high rainfall events of 110 millimeter per hour, but the ERA 5 hourly analysis produces maximum about 30 millimeter per hour. That's all. So therefore, you cannot train your AI model on that data and
Correct.
then hope to predict the rainfall. So, but where do I get that better data? Now, what is the problem of ERA 5? ERA 5 problem is that they use, when you produce this 1 hour analysis, there is a forecast model that goes into the analysis, right?
Right.
Reanalysis has a forecast model, weather forecast model. But the weather forecast model, to make those 80 years of hourly analysis, they made the weather forecast model was a version of the forecast model which was hydrostatic forecast model, not the non-hydrostatic. Non-hydrostatic forecast models are required for actual forecast, and that is what is done. High resolution, when they do on real time, they use a non-hydrostatic model, because but to do the reanalysis, they were focusing mostly on the large scale, and they said that okay, at least large scale they will do better. But rainfall, they messed up, because the hydrostatic model cannot. Why they cannot do that? Non-hydrostatic model doing these hourly analysis over 80 years period takes a huge computational time, because non-hydrostatic model requires small time step, and those every time you have to make those analysis, and those, it seems apparently takes a lot of time. So actually you have to make about 1 or 2 or 3 hours forecast, and those forecasts are required, and even that for 80 years hourly time scale takes a lot of computation, and people are not willing to invest that, and even today we don't have that. So that is one thing. We will have to do similar 1 hour reanalysis for 80 years or more using a non-hydrostatic forecast model. Then you will have a set of data where hourly data, then precipitation can be trained. So that is one important requirement, and nobody is doing it right now because it is a bit expensive. The other possibility is we need systematically, we need see observation data, precipitation data we might have, but that data is also, now today we have observation and precipitation data. It's very high resolution observation data, is about 10 kilometer global observational data is available from satellites called IMARS and CMOR. Okay, these data is very good, but they are only for 25 years. I don't have. Even if I had even if I had observational data for 100 years, then what the problem is that I have to train them with also the large scale circulation. This large scale circulation has to come from Irafile again. Okay. Okay. So circulation is good, but circulation and rainfall has to be consistent, because rainfall and circulation are linked, because everything is convectively coupled. But if I have an observation data which is independent of the reanalysis, then I cannot actually use it very well. So that is something that we are now working on. Actually, this is a project, research project, where we are making observations called surrogate observations of rainfall by augmenting the observed data, and then trying to see if I can use this observed data of rainfall and ECMWF winds to retrain these models for better rainfall prediction. I don't know whether it will work or not, because there will be some inconsistency. But inconsistency may be okay, because we are looking at the diversity in the relationship. No, so it doesn't probably matter. But we have to try. We don't know that. So these are research problems, and this is actually requires huge data handling. So other issue is this augmentation itself, how to augment the observed data into a large volume. That we have been able to do to some extent. So these are all testing some of it, some things we are testing, but there are issues. These people are now ECMWF, as I said the last slide, that they are already trying to simulate precipitation in a different way, train them in a different way. So those are, and the precipitation training requires another problem, because precipitation is a positive only quantity, okay? But when you convert it into patterns, then when you do, then you have to, you are talking about precipitation anomalies, right? So then actually it cannot predict real precipitation. Sometimes it will predict precipitation which is negative. So you need to put a constraint in your training that precipitation could not be negative. And that is another, so technological issues are there, and ECMWF is trying to do that. So like that, there are different ways of training, and the AI development of the AI models themselves have to change in such a way that these constraints are built into the system. How do you build? So inside those, some layers have to be put where the proper filtering will ensure the constraint. So these are actually a AI developmental issue, a model developmental issue that needs to be also worked on. So there are many issues like that, and there is lot of fundamental work is required to improve this.
Thank you, sir.
And we are not just thinking about it.
Sir,
Okay.
a
Go ahead.
related question is that AI is more data intensive, and the extreme events, their frequency is very less compared to the large time series. So is it that people are thinking that AI may not have enough data of the extremes, and it is still not good for forecasting extreme weather?
Exactly. Well, it is, and that is what I'm saying, that we need more data to train. And right now we don't have, because first of all, the available analysis which is consistent with rainfall, available reanalysis, poor rainfall extremes built in them, very poor. So those rainfall extremes, we cannot train and get the observed rainfall extremes. So there is no way that. So I need, that is where I need, if I have 100 years of good hourly non-hydrostatic non-hydrostatic model reanalysis, then I think I will be able to train them for extreme events also. Extreme
Okay.
events at certain scales, depends
Okay.
on what scale. See, sometimes people will talk about, I want to go into the nowcasting of 1 kilometer scale, and 1 kilometer scale may be very difficult because you won't probably have any data to validate them. But 10 kilometer scale, we have this rainfall, observed rainfall data. So we can actually validate them and correct them. So basically, I developed, suppose I had have a non-hydrostatic model analysis. The non-hydrostatic model will have its own bias and everything, but they are consistent. Rainfall and winds are all consistent. So therefore, I train them, and then retrain the precipitation on observed data. Observed data, when I retrain, the model will correct the bias. So therefore, once that bias is corrected, even the 10-kilometer scale, I think we will get very good extreme event. Extreme, but it will have to be probabilistic again. So we develop a probabilistic version of this model. So extreme events cannot be predicted deterministically, because they will, as I said, a small error in the initial condition will make it move away from in location 1 or 2 grid points, or in time 1 hour ahead or 1 hour later. All these things will affect a large error in deterministic forecast of the extreme event. But probabilistic forecast can be significantly improved, and that is what European Center is also just beginning to show that.
Thank you, sir. So I wish to take 1 or 2 questions from colleagues.
Yeah,
So
so
Professor Sahu, you may ask.
yeah, thank you, Narendra. So thank you, sir, again for very interesting talk. And I have a couple of questions. Just one question is that when I see the evolution of forecast performance, and particularly between 1995 to 2000, that is if you see the transition in performance, that also looks like a kind of revolution. So, just I want to know what were the factors which brought such a sharp, change in the forecasting capability.
Can you repeat that again? I just missed something.
Yeah. So, if you see the forecasting performance, the evolution from 1981,
Correct.
and if you see the period between 1995 to
Oh yeah,
2000,
yeah.
there has been a big, significant improvement. So that is kind of revolution again. So what were the factors which we can attribute to this transition?
Okay, I'll tell you something. Yeah, it is very, very interesting question. And there are a couple of things actually here.
Yes.
Okay, let me go back to the beginning. This figure is better. Okay, so here you see this part you are meaning here from here.
Yes.
Okay.
Yes.
Right. This is when in 2000, that is when what is called direct assimilation of radiance. So what does the satellites do? Satellites have lot of microwave radiometers. Okay, the microwave radiometers get radiance. So they are mostly passive, and some are maybe active, but you get radiance, some radiance. Now radiance is coming from some temperature or some water droplets, or temperature of that water droplets, or and from that you derive by using the relationship between temperature and radiance. So it is there is this law by which this temperature is fourth power of radiation, total radiation, and then maximum radiation takes place at the as goes as inversely as the temperature of the black body. So based on those is you can actually calculate what the temperature is. So normally to do that correctly, temperature to get the temperature profile from the data from the you have to go back to a model. That means there is a one-dimensional radiative transfer model. Then you use that radiative transfer model to give you the temperature and bring the temperature into the equation. So instead, now they have built in this radiative transfer models into these. So once the radiation is given, directly it goes into the model, and that model is now assimilates radiance rather than and that made a big difference. And that is the time when also the large number of these microwave radiometers have come into the space. Many satellites, many microwave in large number of bands. So hyperspectral radiometers have come in. As a result, your temperature profiles become very, very accurate and large in numbers. So these two things in the extratropical systems have are geostrophic. So once you have a very good large scale vertical profile of temperature and in many, many places, it gives you the winds also, estimate of the winds properly. Because winds are geostrophic in Milan. The temperature gives you the pressure information, and the pressure information, pressure variations in space gives you the wind information. So both winds and temperature become very good. And as a result, the forecast capability improved. So some of the errors in our initial thing, and these are two important things. So this, you see, this has happened when sudden hemispheric. So by the way, I forgot to mention in the beginning that these two curves are forecast scale in the southern hemispheric from 20 degrees south to south pole, and the northern hemisphere from 20 degree north to north pole. So always in the early days, always when satellite data was poor, the large scale data, the observations, they were always much more in the northern hemisphere. So therefore, my initial conditions were much better in the northern hemisphere. Therefore, my skill was always better in northern hemisphere. Southern hemisphere is mostly covered by ocean. So therefore, I had a poor skill. So whether it was like 95, 90, 85% in northern hemisphere, it was like 70% in southern hemisphere. That bad. But as soon as my these hyperspectral radiometers became so much available, and their retrieval, temperature retrieval, become more and more accurate, because more spectral resolution gives you better vertical profile. You can correct those errors in the retrieval, and so that made a huge difference. So all this is because today the best of the forecasts are is largely contributed by the satellite data, and so that is the importance of satellite data. So this sudden jump is due to large number of observations coming from satellites, and so it improved much more in the southern hemisphere than in the northern hemisphere. Northern hemisphere it improved, but not as much as this southern hemisphere suddenly jumped. Okay. And that it became as good as the northern hemisphere. Yeah. So although there is very little actual observations, you see, their surface observations are very little, but still they are making as good as the northern hemisphere. That is this. Is the impact of satellite observation.
And a small question related to the AI-based forecast is how in a rapidly changing climate scenario, the feedback process is very important. So AI is not trained because there is no data. So AI is not trained for the feedback processes. So how is it going to deal with in AI?
As far as weather is concerned, it is not going to change very much, because the weather is a short time scale, na? And the short time scale, we are if we have good data, we can train and we can get away with it. The ocean atmosphere feedbacks become more important on seasonal time scale, on the longer time scale. So all those, the other problem that we have is that this the prediction of the intra-seasonal oscillations and this climate. That is the S2S model. So right now, that is an area of active consideration. Now the people are trying to develop, and the first S2S model has come, a Earth system model, where ocean and atmosphere have been linked. A data-driven Earth system model is come from the Max Planck Institute. They have come up with the first, and they have been able to simulate these for about 800 years. So this kind of a climate model has now come. And in that climate model, now actually we are trying to assess how this climate data-driven model is simulating the intra-seasonal oscillation. And we find that there are considerable, they are not as good as the weather. There is much more error in the intra-seasonal oscillation. When the data-driven model is the intra-seasonal oscillation and the seasonal mean, you have to integrate them much longer now. That means it has to, data-driven model has to build memory of how it is related. Today's weather is related to 40 days earlier weather, because that is the evolutionary cycle of inter-seasonal oscillation. For seasonal mean, it has to at least 90 days ahead, or 120 days ahead. You should be able to have the large, at least the statistics of this must be correct. So that is where a lot of work will be required, because that is still not happening. But at least we are now have a stable model where the ocean atmosphere can be coupled, and that coupling has allowed it to integrate. But we find that the energy, the kinetic energy or the amplitude of these systems decrease with forecast time in that time scale. So a lot of work is required in that. So it is in the beginning. It is just the beginning.
Yeah, thank you. Well, so Naren, over to you if there are other questions.
Okay, so there is one question from Professor Som Kumar Sarma. Sarma ji, please ask.
Okay, thank you, Naren. Sir, very interesting and fascinating talk. Thank you so much. This is Som Sarma from PRL. Sir, this, I want to know that in that our forecasting the patterns, how much role is there for uncertainty in the vertical distribution of clouds and cloud types?
Right now, I think that question is not known. The answer to that question is not known, because we are not trying to resolve clouds and cloud types so much at this point. But I think slowly people are beginning to add. The European Center has now added different types of clouds and so on. But because if you have all the clouds, the data is required of different types of clouds at that resolution. So there are issues with that. But operationally, if we have to do, finally, we have to add all those, because you have to also require to have the constraint on precipitation correctly. You need all the components of the things that go into the precipitation. Components like clouds, types of clouds, the height of the clouds, and all those things will be related to the actual precipitation. And so we need that when to improve precipitation, we have to include all those. But then training them becomes a issue. And as far as my knowledge is that there is not enough good data to train them. So you need again good data from high resolution non-hydrostatic model simulations to train them. So best thing will be to do that. So suppose you have a non-hydrostatic 1 kilometer global model which is run for let us say 30 years, and use that data to train the. So once I have that, then I will have all kinds of things. Everything will be there, like different types of clouds will be there, the moisture content, this, that, everything will be there. So that is the first thing. The second question that you have asked, the uncertainty, is a very more difficult question. First, we don't have even enough data to train. So the uncertainty will be always there. But to get to the uncertainty, what we need to do, we have to do probabilistic forecast. So I can do probabilistic forecast and see what is the kind of uncertainty that we have in the probability distribution. From the probability distribution, we can get some idea about the uncertainty. So, and this data-driven model, just like the weather prediction models, we can actually make a large ensemble of forecast, including all these variables, and then see how what is the kind of uncertainty that is there. But first of all, I think we need to have some idea of the bound on the uncertainty for observations. Do I have a good bound on observations? I don't personally. I'm not very knowledgeable in this, but we need to have that, and then only we can say that okay, we are within the bound that is within this relationship. So I think this is a more difficult question.
Okay, thank you very much, sir, for very interactive and very nice talk. Thank you, sir. Thank you.
Thank you.
Thank you, sir. So now I will request my colleague Dr. Vineet Goswami to formally conclude this session. Over to Dr. Vineet.
Thank you.
Thank you very much, Narendra. I hope I'm audible.
Yes,
Yes,
yes.
yes, yes.
Okay, thank you very much. Yeah. So thank you very much. So that brings us to the conclusion of the 114th episode of PRL Amrut Vyakhyaan. So first and foremost, I would like to express my gratitude and heartily thank to Professor B.N. Goswami for kindly accepting our invitation and giving an excellent talk on weather and climatic forecasting and prediction and the way forward and various challenges involved in this issue. And so I would also like to thank Professor Goswami for answering the audience's questions so nicely. And next upon, I would like to thank our audiences present in today's forum. Next, I express my sincere thanks to PRL Director, Professor Anil Bhardwaj, Dean PRL, Professor D. Pallam Raju, and Chair and Co-Chair of PRL Amrit Vyakhyaan Committee for all their support and encouragement in organizing this episode of PRL Amrit Vyakhyaan successfully. So do visit our website and other media platforms to know about more events being held at PRL, in particular this event, PRL Amrit Vyakhyaan. And with these words, I propose for the closer of today's episode of PRL Amrit Vyakhyaan. Thank you, everybody.
Thank
Thank you,
you.
Vinit. Thank you.